Good morning students, welcome to the video lecturing on groups for the BSc third sem mathematics. Let us take one theorem. If order of A is equals to n and P is relatively prime to n, that is GCD of P and n is equals to 1, then order of A raised to P is equals to n and it is equals to order of A. Let us take proof. Suppose let us take order of A raised to P as here m, and we have to prove here this is equals to order of A. So that is, let us take order of A raised to P as m. Then this implies here with the definition of order of an element, we know here a to the power of P whole raised to m is equals to E. This is the definition of order of an element. By data, what is given here? Here it is given that order of A is n. So this implies again from the definition of order of an element, A raised to n is equals to E. Then this implies here raising the power P on both sides. A raised to n whole raised to P is equals to E raised to P. So it is equals to A raised to n whole raised to P is equals to E raised to P means E into E into E. P times you have to multiply, and we know E to the power of P is again E only. And this implies we can interchange these two here. We know a to the power of m whole to the power of n is a raised to m into n. So we can interchange these two. This is nothing but here a to the power of p whole raised to n is equals to e. So again you go back the definition of order of an element. Then this implies here order of a to the power of p is less than or equals to this n. So this may be less than or equals to it is. This implies here we know order of a to the power of p, here we have taken as m. So let us substitute that one. This implies here m is less than or equals to n. This is from equation number 1. We have taken this one as equation number 1. Next here it is given that here what is given? This is GCD of P and n is equals to 1 is given. Let us take here, since P is relatively prime to n, that is GCD of P and n is 1. So relatively prime means what here? They don't have any common divisors. The common divisors of both P and n is 1. So this is the GCD. You know GCD means here the number which is if you divide these two numbers by a common divisor, then we can call that one as a GCD. So this implies here we know this you studied this one. If the GCD of P and n is equals to any, it is this is one this one statement we know you studied in your previous class. If GCD of x and y is equals to d, and this implies here x into a plus y into b is equals to d. This is one statement we know here. So using this we can write this one as here any integer, it is x is any integer here, x and q are any integer. So this can be taken as here p into x plus n into q is equals to 1 for some integers. This x and q I have taken here, no? So whatever it may be, this is only integer it is. We have to take here this one as integer. So this is equals to this. Therefore here now let us take a. This a can be taken as a raised to 1, and this is equals to, here we know 1 can be taken as here px plus nq. So a to the power of px plus nq, it is equals to again we can separate these two, a to the power of px into a to the power of nq, and it is equals to a to the power of px into a to the power of nq can be taken as here a raised to n whole raised to q we can write. So this is equals to a to the power of px as it is. This a to the power of n is nothing but here we know a to the power of n is equals to e, because order of a is n. So this implies a to the power of n is equals to e. This we know here a to the power of n is equals to v we have here. Let us substitute that one. So this is e to the power of q. Again we know a to the power of q is e only. So and e is any this is the entity element. So a to the power of p in x into e is again a to the power of px only. This implies here we know a is equals to a to the power of px we got. So that is a is equals to a to the power of p whole raised to x. We can write this one as here. Now raising the power m on both sides. A raised to m is equals to you write this one as it is whole to the power of m you take. This is a to the power of p. We can multiply these two powers. So it is a to the power of p whole raised to m into x. So again we can take this one as here a to the power of p. We can interchange these two here m raised to x. So this is equals to here again we know a to the power of p whole to the power of m is nothing but what here? e, because here we have taken, here we have a to the power of p whole raised to m is equals to v. This is from equation number 1. So this is a to the power of p whole raised to m is e, this is e to the power of x. Again we know e to the power of x is e only. This implies a raised to m is equals to e. Again you apply the definition of order of an element. So this implies order of a is less than or equals to m. So this implies here we know order of a is what? Order of a we have taken here as n. So that is order of a is equals to n, we know here. Let us substitute that one. This implies here n is less than or equals to m. Take this one as equation 3, and here we have equation 2. Equation 2 is m less than equals to n. So from equations 2 and 3 what we have here? M is equation 2 is m is less than equals to n, and equation 3 is m is less than equals to m. So from these two we can say that here m is equals to n, and we know m is nothing but here order of a raised to p, and n is nothing but order of a. So this implies here order of a raised to p is equals to order of a is equals to n. So this is the proof of this theorem. Let us take one more theorem. If order of a is equals to n and GCD of p and n is equals to d, then order of a raised to p is equals to n divided by d. So the meaning of GCD is like this. Just now I will tell you. So suppose we have two divisors. So suppose we have two numbers here. Let us take 8 and 18. So the divisors of 8 and 18 are here. So let us divide. We can divide 8 by what? 1, 2, 4 and 8. And divisors of 18 are 18 can be divided by 1, 2, 3, 6, 9 and 18. So here common divisors are what? What are the common divisors? 1, we have 1 here also, here we have 2, here also we have 2. Only these two are common divisors. So in these two, the greatest one is here what? 2. So this is equals to 2. This is the meaning of GCD of two numbers. So here suppose if order of a is equals to n and GCD of p and n is equals to d, then order of a raised to p is equals to n divided by d. Let us take proof. Suppose order of a raised to p is equals to m. Then this implies here, because we are proving this one, no? So you have to take order of a raised to p. This implies here definition of order of an element, a to the power of p whole raised to m is equals to e. Now given d is equals to, here it is given d is equals to GCD of p and n. And this implies here, so this is again from the definition of GCD of two numbers. So this d divides p and d divides n. So means d is the divisor of p and n. We know here in this example you can observe this one. So d is the divisor, means 2 divides 8 and 2 also divides 18. So this is the meaning of that divisor. So this implies here what? 2 divides 8 and 2 divides 18. Same thing we can apply here also. This implies here d divides p and d divides n. This implies again the definition of a divisor. So definition of a divisor here, this implies p is equals to d into q1 and n is equals to d into q2. This is again from the definition of a divisor, where p and q are relatively prime to each other. So again this meaning of this one means divides means here what? Just now I told you here. So here this 2 is the divisor of 8 and 18, no? So it means what here? 2 divides 8 means we can express the definition of a divisor means here, just now I told you this 2 is the divisor of 8 means what? Here we can write this one as here, this is again, so we can write this 2 divided by 2 divides 8 means we can write this one as here. This implies 8 is equals to 2 into 4, that is it is in the form of this one. So here d divides p means p is equals to d into q1, no? It is also same, it is in that form only. P divides this is d divides p. So here p is 8, no? You can compare these two. So we can write here 8 is equals to 2 into some integer. So here also same thing here. p is equals to d into some integer, and here n is equals to d into some integer, where GCD of these two is equals to 1. Now here it is given a to the power of p whole raised to m is equals to e we have taken here. Then this implies here a to the power of, we can multiply these two, p into m is equals to e. Take this one as equation number, this one as equation number 1. Since here again order of a is n, it is given order of a is equals to n. This implies here, this implies in previous theorem we have studied this one as here n divides p m. So this implies here, this implies d into q2. So here n is equals to what we have here, we have this n. So n is equals to, here we have d into q2, which divides this p is d into q1 into m. This is from equation number 1. So this is equals to, here both are d get cancelled, it is q divides q1 into q2 divides q1 into m. This implies q2 divides m, because this is GCD of q1 and q2 is equals to 1. So we know here if the GCD is equals to, this implies here q2 divides q1 and q2 divides m. Since GCD of these two is equals to 1, we can take this one as here q2 divides m. This is again the property of this divisors. This is studied in our previous classes. Let us consider a to the power of p whole raised to q. This is equals to a to the power of p into q2 we can take, and this is equals to a to the power of p into q2 is equals to, you substitute the value of p and this one, p is dq1 into q2. This is equals to a to the power of dq1 into dq2 you take here and into q1. So it is equals to a to the power of n into q1, because here dq2 is nothing but, here we know dq2 is n. This is n into q1, and we write it as a raised to n whole raised to q1. This is equals to a raised to n as e to the power of q1. So therefore this is nothing but, here a to the power of p whole raised to q2 is equals to e to the power of q1 as again e only. So that is here we know from the definition of order of an element, this is order of a to the power of p is equals to m, and this is we have taken here order of a to the power of p as m we have taken here, and what we got here as a to the power of p whole to the power of q2 is equals to e we got here. So this implies here, m divides q2. This m divides here q2 by previous theorem. Take this one as equation number 3. So from equations 2 and 3, here we have q2 divides m, and in equation 3 we have m divides q2. So from these two we can say that here q2 is equals to m. And now equation 1 implies here, in equation 1 what we have here, n is equals to dq2 and p is equals to dq1. So n is equals to dq2 we have here. This implies here n is equals to dq2. q2 is nothing but here m. So this implies here m is equals to n divided by d. So this implies what we have taken here m as, we have taken m as here what? We have taken m as order of a to the power of p. So this implies here order of a to the power of p is equals to n divided by d. This is the proof of this theorem. Let us take one last theorem in this properties of order of an element. That is, take the statement, in any group G, order of A is less than or equals to order of G. So order of an element is always less than or equals to order of a group. Order of a group means number of elements in that group. For all A belongs to G it is. Take proof. Let us take order of A is equals to n. And this implies here, apply the definition of order of an element. Then this implies A raised to n is equals to E. Take this as equation number 1. Let us take some set H is equals to a square, a cube, etc. a raised to n. It is equals to E. Be a subgroup of group G generated by an element A. So group generated by an element A means here all the elements of this group are in terms of multiples of A only. since H contains n elements, because we have here n elements, then order of H is equals to n. Take this one as equation number 2. Here we have two cases. Subgroup means it is subset and it may also equal to the same set G only. Let us take case 1 when subgroup H is equals to same group G. Then this implies here order of H is equals to order of G. We have taken here as order of H as n because we have taken n elements in that. This implies here n is equals to order of G. So n is nothing but what? N is nothing but we have taken here as order of A. And this implies here order of A is equals to order of G. Take this one as equation number 3. So now let us take case 2. Case 2 is when H not equals to G. Because here H is a subgroup means first point is H is a subset of G. After that H is also a group under the same binary operation defined in G. So it may be subset means it may be equal to G and it may not be equal. So we can let us take here H is not equals to G, second case. So in this what happens? H is not equals to G means order of H is less than order of G means there exists at least one element in G which is not in H. So this implies what here? We have taken order of H as n. So this implies n is less than order of G from equation number 2. Because here in equation 2 what we have taken? We have taken here as H contains n elements. So order of H is n. So now let us combine these two equations. Combining equations 3 and 4. In equation 3 we have order of A is equals to order of G. And in equation 4 we have order of A is less than order of G. So from these two we can say that order of A is less than or equals to order of G. So that is order of any element of a group cannot exceed that of a group. Means order of any element of a group is always less than or equals to number of elements in that group. So this is the proof of this theorem.